Let's take a look at this check on spontaneity. We're going to start by evaluating entropy, which is delta S. It's the disorder or randomness. And in our first question here, we are asked to evaluate some different systems. So it says determine if entropy increases, decreases, or stays the same for each of the following processes. You're not asked to calculate anything. We just want to know what happens with entropy. Are we increasing or decreasing the disorder or randomness of this situation? So in the first one, we start off with a solid, and we're moving to a gas. So if we have a solid, we think of those molecules being really close together, okay? And then we're moving into the gas state. So for a gas, remember those molecules are expanding out all over the place and moving in all sorts of different directions. And so because we go from a more organized system to having all of these chaotic molecules all over the place, this is actually going to be increasing. Okay, so we're going to increase entropy. And increasing entropy is a positive delta S. All right, in the next one, we have sodium and chlorine gas. So solid sodium and chlorine gas are being reacted to form sodium chloride, which is a solid. And so what we have is we have two sodiums on the left side. Change my pen. So I have a sodium and I have another sodium. And we're kind of doing this particle diagram, and then I have a Cl2. Maybe we'll do this. Cl bonded to another Cl. And this is one entity because they're bonded together on the left. And then on the right, I end up with two sodium chlorides. So I'm going to have an NaCl bonded together, and then I'm going to have a second NaCl bonded together. And the question is, does this increase or decrease the entropy? So is it more or less random or disorderly? And so in this case, we go from 3 particles, okay, so 3 particles or pieces, down to 2 particles. The other thing that we can look at is this one here is a gas, and so we go to having a gas to no gas. And so there's a couple different ways we can look at that. And so because we're reducing particles and we're reducing the amount of gas, this is actually going to decrease entropy, or a negative delta S. In the third example that we have here, we have sodium chloride that is going to be solid. So we're going to have NaCl as a solid in a fixed position here. And then on the other side, we're going to put that into a beaker with some water, and we're going to, let's get some water in there. There we go. We're going to have those sodium and chloride ions split apart from one another. And so we're going to end up with an Na plus and a Cl minus. And so we went from 1 particle to 2 particles that are further apart from one another. And so this is going to increase entropy. Okay, so that's a little bit on entropy, and then we're going to use entropy and plug it in to be able to determine free energy. And free energy is the energy available to do work. So if we have some energy available to do work, then that particular chemical process can do work. And if we don't, then we have to apply some energy to get that process to occur. You'll learn a little bit more about that as you get into biology, and then we come back around and do more with this when we get to AP Chemistry. Okay, so our equation is delta G is equal to delta H, so our enthalpy, minus the temperature, T, times the entropy, delta S. Okay, and it's all three of these factors that tell us what's going on with this. So we might want to know a couple other things. So if it's a negative delta G, that's what causes us to have a spontaneous process. Meaning it's going to happen on its own without any extra outside work. There's free energy available to do the work, and so it will happen automatically. If it's a positive delta G, it's non-spontaneous. And if delta G is equal to 0, then the system is at equilibrium. So those are just some things that might be good to know later. As far as the problem solving with these, you're really just given the values and asked to calculate delta G at this point. So let's go ahead and do a few of these. Okay. So the first one says, it says determine the free energy for each of the following processes. And so we're just calculating delta G. When we do this, though, you need to take a look because this one is in kilojoules and this one is in joules. So we need to get those to be the same. In order to do that, I can just divide this number by 3 or move my decimal place 3 places over, and I can get that to be then into kilojoules. And so we're going to have our negative 23.6 kilojoules minus 972 Kelvin, that's pretty darn hot, times 0.647 kilojoules per Kelvin. So kilojoules is going to cancel. We're going to cancel, or excuse me, not kilojoules. Kelvin is going to cancel because we're multiplying, and that leaves us with kilojoules. And so we'll do our negative 23.6 minus, in parentheses, 972 times 0.064, oops, not 0.6, 0.647. There we go. I got all my numbers right finally. Okay. And we get negative 652. Did I plug that in right? Let me double check my numbers. Nope, I transposed a number. Hold on. Negative 23.6 minus 972. Oh, no, I did that right. I transposed them on a key that I had for myself to double check. 0.647. Let me just double check that number one more time. There we go. So with sig figs, we can round that. This number originally didn't have any place values right at the decimal, so I'm going to round that to negative 652 kilojoules. This one. There we go. All right, let's take a look at the next one. Go a little bit faster. And it just so happens that this first one would be a spontaneous process. I guess I should have written that. So this one is spontaneous. For the next process, we have a positive value for delta H for our enthalpy, so 38.2 kilojoules minus 115 Kelvin times, and we're going to divide this, so our decimal will go here, and that'll make that kilojoules, negative 2.480 kilojoules per Kelvin. And I went ahead and did that earlier. Hopefully I have those right. So 323 kilojoules. And this process then is a positive value, so that would be a positive value, and that makes this non-spontaneous. Okay. The last one, we'll just go ahead and plug those values in. So delta G, negative 42.8 kilojoules minus 273 Kelvin times, so we're going to move that decimal place 1, 2, 3, so I'm going to have a 0 here, so negative 0.0181 kilojoules per Kelvin. And our delta G for this one is going to be another positive value, 286 kilojoules. Since it is positive, this one is also going to be spontaneous or non-spontaneous. So the question becomes, even before we get any of that data, can we make a prediction about what we're actually going to see? And so when we call a process spontaneous, a lot of the times we'll say that it's thermodynamically favorable. So let's fill in this chart. If we have a negative delta H and a negative delta S, or excuse me, a positive delta S, we will always end up with a negative delta G. No matter how we do that, we are always going to end up that way. And so it's going to be favored or spontaneous at all temperatures. Okay. If we have a positive delta H and a negative delta S, and you can actually plug these values in with simple numbers and confirm that using the equation, delta G is always going to be positive then. So this is not favored at all temps, so it's always going to be non-spontaneous. Okay, and then the question becomes, well, are there times where it could be either? Yes, absolutely. And so if we have a negative delta H and a negative delta S, we may not know what's going to happen here. Okay, and so the driving force in this one is going to be based on temperature, and so we're going to end up with a favored system or spontaneous, favored negative delta G at relatively lower temperatures. Okay. And it would be non-spontaneous at higher temperatures. And we don't have to evaluate those values quite yet. We will do that in future years. Okay, and then if we have one that both of them are positive, then this will be favored at high temperatures. And so we can plug those numbers in. So favored, okay, that negative delta G at high temperatures. Okay, and that's it.